Hello friends, welcome to my channel. Today we are going to discuss a topic which is metal clusters. As we all know that metal cluster is a very important topic in exams like CSIR NET, GATE, IIT JAM and all other national level entrance exams. So let's start. So as you know that what is metal cluster? So metal cluster is a group of two or more metal atoms which are connected by a direct metal-metal bond. In most cases there will be metal-metal bond, but there are few cases where there will be no metal-metal bond present. So in this video we will mainly talk about metal carbonyl clusters and its derivative. So as we know, what is carbonyl metal cluster? So carbonyl metal clusters are of two types: the no nuclearity carbonyl metal clusters LNCC and other is high nuclearity metal carbonyl clusters which is HNCC. So the condition for LNCC is that the n should have value less than equal to 4, where n is the number of metal atoms present in the cluster, and the HNCC should have the value of more than 4. Okay, so we will in this video we will mainly talk about LNCC. So just you have to know that for LNCC the metal atoms present in the metal clusters, they have to obey the 18 electron rule. So what is 18 electron rule? 18 electron rule is that every metal atom present in that complex will have to have 18 electrons in its valence shell. So the next question is how to find the metal-metal bonds. So if you correctly observe the previous year questions of CSIR NET or GATE exams, there is every year there will be a question of this type, that they would given a few complexes, then they will ask that how many metal-metal bonds are present. Okay, so there is a trick to find how many metal-metal bonds are there in the metal-metal clusters which have LNCC type of complexes. So the step 1 for that will be that we have to first calculate the total electron count of the cluster, which is A. So A is consist of number of electrons in the valence shell of the metal atoms. There will be more than one atom, plus there will be number of electron donated from the ligands, and again that will be added to the charge of the complex. If the metal complex is positively charged, then the charge would be subtracted from the value, and if it is negatively charged, then the charge will be added. So the step 2 is to calculate B. So B is designated as n into 18 minus A. So where n is the number of metal atoms in the cluster. So after that you have to calculate C, that is C is designated as B divided by 2. So the C actually denotes the number of metal-metal bonds present in the cluster. So now we will discuss a few examples, at first some simple examples. After that we will solve some previous year questions which have been asked previously in CSIR NET or GATE exams. So now we take an example of no nuclear metal cluster. So first example is Fe2CO9. So according to the rule we will first count the total electron count. So from the metal there is 2 iron, and the valence shell of the iron there is 8 electrons, and each ligand of carbon monoxide donates 2 electron. That will be into 9. So what we get? 16 and 18 we get 34. So after that there is 2 metal center, that is 2 as 2 metal. So that will be, so we have to get B, which is 2 into 18 electron minus what we get from total electron count, that is 34. Now we will get 2, and the number of metal-metal bond we get by dividing B by 2, we get 1 because B is 2. So there is one metal-metal bond present in Fe2CO9. So the structure will be like this. There is one metal-metal bond, and there is 9 ligand. One of the possible structure is this, one bridge center. So one of the probable structure will be like this: 3 bridging carbonyl and 3 to each center, each metal center. So we will get the structure, and so this is the one of the most probable structure. You can also draw one bridge ligand carbon monoxide and 4 terminal carbonyl at either side. But the most important fact which asked in CSIR net, that is the number of metal-metal bonds. You have to just calculate it out. So next example is CO4, cobalt 4, carbon monoxide 12. So now we again count the total electron count of this complex. So 4 into cobalt has 9 electron in its valence shell and 2 for each monoxide, carbon monoxide, into 12. So we get 36 plus 24, so 60. So that is A. Now there is 4 metal centers, so 4 into 18 minus 60. This 4 into 18 is 72. We get 60, so we get 12. So now for the number of metal-metal bonds, we have to just divide 12 by 2, that is 6 metal-metal bonds. So what could be the probable structure? That will be like this: 1, 2, 3, 4, 5 and 6. There will be 6 metal-metal bonds among the 4 cobalt molecule. So rest of the ligands you have to just distribute it out. Okay. So that is the rule of which you can count the metal-metal bonds. So next example is iridium 4, carbon monoxide 12. So this question has been asked many times in many format, and with different types of questions has been asked in CSIR net. So we all know that iridium is in the same group of that of the cobalt, just higher molecular weight. But here is the fact that for the iridium there is no bridging carbonyl. For the cobalt there could be bridging carbonyl present, but for the iridium there is no bridging carbonyl. Okay. For cobalt or its higher conjugats like the same group, and it is also true for other groups like iron. Okay. The reason is that to form a bridged carbonyl or a bridge bond, the metal center has to come significantly closer, and if you go down the group, then the metal orbitals or the size of the metals are higher, goes larger in the down the group. So for that reason, the bridged carbonyl or any bridged bond are not generally formed for the higher conjugat of the group, of any group like carbon, like cobalt group or iron group. So for iridium there is no such bridged carbonyl. So it is asked in CSIR 2013, maybe December, that how many bridged carbonyl. So the rest is identical with that of the cobalt because the electron counts are same as they are in the same group. So next example is, so for this complex we first have to count the electron counts. So there is 2 carbonyl, so 2 into 2. So there is Cp, that is cyclopentyl ring is there, so that do is 5 electrons. Rhodium, which is in the same group of that of the cobalt, that's 9. That is into 3. Oh sorry, there is another free carbonyl of their complex there was, so plus 2. So electron count will be 4. This is 14, 42, there is 2, so it will be 48. And now there is 3 metal center, so that will be 3 into 18 minus 48, so 54 minus 48, we get 6. So number of bonds will be 6 by 2, that is 3. So the structure will be like rhodium, rhodium, rhodium. There will be metal-metal bonds, 3 bonds. So now what happens? 2 of the carbonyls are bridged because mu CO. and one carbonyl is free, so this one will have this carbonyl, and after that each rhodium will be connected with cyclopentadiene ring. So I will solve the 18 electron rule by neutral atom method. Assume all the atoms are neutral, so it doesn't concern cyclopentadiene anion. I just consider it a neutral, that is 2 electrons 2 to 4, and there is a single electron is here, so I choose the neutral convention. So in this case no metal have any valency here, just you have to choose a neutral electron count of every atom. So you can also solve it by charged ion atom method, but I prefer neutral method more easily. So next example I will discuss, it has previously appeared in CSIR exam. So this is the problem, so you have to just put the options back to back so that you can answer it. So from the first option A we get the number of ions in the metal 4, from the carbonyl 12, and from the charge 1 we get 70. That is not satisfying 18 electron rule. So from the option B electron, there is 5 electron in the metal, 12 from the ligand, 1 from the charge, about 18. We get the right answer, but just take it out the rest of the options. So electron count from the metal is 9, from the carbonyls is 8, charge is 2, so we get 19. So this is not correct. So next example is from the metal, there is 6, from the carbonyl is 10, from the charge is 1, so we get 17. This is also not correct. So only option B gets the 18 electron satisfied. That is the answer. So I have just written down the complexes which have so far came in CSIR NET exams one by one. So I have chosen those complexes for which to count the total electron count is difficult or somewhat tricky. So let's start from the first example. So here we can see that there is eta 5 cyclopentyl ring, diagonal ring, and there is ruthenium, chlorine, carbon monoxide, and PPH3. So from here we get 5 from ruthenium, from the valence electron count, that is 8, from chlorine according to neutral atom method it contributes 1, from the carbonyl we get 2, from the PPH3 we get 2, so we get 18. So that is 18 electron satisfied. Now here from the tungsten, number of valence electron is 6, from the 3 carbon monoxide we get 6, chlorine will contribute 1, SiMe3 also contribute 1, because from the silicon there is 1 electron which is not participated in bonding, rest of the electron count participated in bonding with Me3, so that this is why that is 1 for SiMe3. And there is NCMe2, so just write the structure. So this is the structure, sorry, the 2 is outside, okay, NCMe whole twice 2, so we get this, that is MECN, that is a methyl cyanide, okay, so that is 2 there, so that just donates this lone pair just donated to the metal center, so that is 2, so 2 of that donate 4 electrons to the metal center, summation will get 18. Now for this complex we have iridium that will donate 9, 3 chlorine that will donate 3 according to neutral atom count, 2 PPH3 that will donate 2 into 2 4, and there is arsenic pH2. There is a confusion because arsenic is in the phosphorus group. 2 of the arsenic, there is a lone pair of arsenic and 2 of the electron participated in bonding with pH, 1 is left alone, so arsenic donates 3 of its whole electron or just 1 electron. That is confusing, but if we take only 1 then that will serve the purpose, because and again there is a negative charge, so there is again 1, so we get 18 electron count. And again, next option is there is osmium. So for osmium we take 8 for a valence shell. And there is again nitrogen. So nitrogen have 3 unpaired electron. Okay, so that will be donated. That is 3. 2 bromine. So that is 2 for each electron bromine. And there is PME3. So lone pair of phosphorus, that will donate 2. So now NME2. So again 2 of the nitrogen participates in bonding. There is lone pair, there is again a single electron. So if one donates, then 1 this unpaired electron. So if I add, so we get 17. Oh yes, there is again positive charge, sorry, negative charge is there. Just add 1, so we get 17. If we add again the 2, then that will be 19. Then so if any case this complex doesn't satisfy the Electron rule. Okay, so just comes for this example. For this example, there was 4 options. So this has to satisfy the Electron rule. So just take M as X electron at its valence shell. So 5 for 5 carbonyl. So we get 2 into 5 plus X plus now this carbene. There is a carbene there. So each of the carbon have 2 electron which is donated to the metal center and participated in bonding. So this carbon have donated 2 electrons. So just 2 into 18. Okay. So we get 6. So those metals of options which have 6 electron in its valence shell would be satisfied. The options were chromium and rhenium plus. That was the correct option according to those options in that question in CSIR net. So the next option was in the question it is asked to find the number of bonds. Okay, so just take the just have the total electron count at first. There is 3 cobalt, so we get 3 into 9, 27. After the CH, so 4 electron of carbon, there is 4 electron from the carbon, but 1 have already participated in bonding with hydrogen, so 3 is left. So 3 electrons here, and there is 9 carbonyls, so 2 into 9 for each carbonyl there is 2 electrons. So after summation we get 48. Now there is 3 metal centers, so we have to calculate 3 into 18, that is 54. Now we have to subtract 48 from 54, we get 6. So if we divide it 6 by 2, then we get 3. So there is 3 bonds. And there is also asked that which group, which ligand form here acts as a bridging ligand. So that answer is CH. It acts as a mu3CH as a ligand. The structure will be like CO, 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 each connected to a metal-metal bond, and there is a CH ligand. So this is just bridged over 3 cobalt metal ions, and each metal ions also have terminal carbonyls also. So our next example is this. So just we have to again here we have to again ask the number of bonds. So again we have to just count the electron count. So for 2 cobalt, that is 2 into 9, that is 18. 2 iron, that is 16. For 11 carbonyl, it is 22. Okay, and now mu4 pph. Now phosphorus has 2 lone pair, 3 valence shell, and 3 other electrons, one of which taken part in bonding with phenyl ring, and the other 2 electrons are present. So what could be the number of electrons that donated in the iron? So in here what happens that according to answer of the CSIR answer, all of the electrons has been donated. So for each pph ligand 4 electron has been donated. Okay, so that's why for our previous example where I was doubtful that should we donate all of the arsenic, 1 electron or 3 electron. So here it was satisfied equilibrium rule just by 1 electron, and answer was like that. Here also the NME2, so for NME2 ligand, the 1 electron only donated to the metal center. But here the case is different. So for each ligand, 4 electron has been donated to the metal center. So there is 2 such ligands. So 2 into 4 we get 8. So now we add it up. Now there is 4 metal centers. So 4 into 18 we get 72. So we have to subtract 64 from 72. So we get so just for finding the MM bonds we have to just divide 8 by 2. So we get 4. So number of MM bonds is 4. So only cobalt and irons are connected by 4 metal-metal bonds. Here the question has been asked that the number of metal-metal bonds and the number of bridge bonds. So just for you have to first count the metal-metal bonds. So to first count the total electron count. So for ruthenium, 2 of the ruthenium, 8 for each. So we get 16. 2 cyclopentadiene rings. So we get 2 into 5, that is 10. 2 carbonyl. So for 2 for each we get 4. This is a bidentate ligand. So for same ligand there is 4 electrons. So added up we get 34. There is 2 metal centers, so 2 into 18 we get 36, which is subtracted by 34. So we get 2 divided by 2, that is 1. There is 1 metal bond is there. According to the options they given from that previous year, there is only one option where, sorry, at first I say that this ligand is acts as a bridging ligand between the 2 ruthenium metal. Just I am showing that. This lone pair is just denoted by this P, and this P denoted here, and that is connected by a CH2. Okay, this is another bridging ligand, but you can expect that there is one bridging ligand in this compound, but according to the options, the only one option have an MM bond 1, which is correct, which we have no doubt. So corresponding to that, there was 3 bridging ligand. So other 2 bridging ligand, cyclopentadiene cannot be a bridging ligand, so there has to be the carbonyl. Acts as a bridging ligand or terminal ligand to each the total electron count of the 18 electron rule will be unsatisfied. That won't be affected. So each of these CP connected to the 2 rutheniums, and there is 3 bridging bonds and 1 bridge ligand and 1 MM bonds. So these are the few questions which have come recently in GATE exams. So the first question, the question has been asked, in the question asked that the number of MM bonds and the nature of carbonyls. There is this frequency has been stated around 1850 centimeter inverse. Okay, so we know that I have given a list of carbonyls, of the terminal carbonyls which have stretching frequency around 2120 to almost 1850. So again the bridged carbonyl, which is mu2 carbonyl, bridged carbonyl have stretching frequency less than that, around 1850 to 1700 range. And after that mu3 bridged carbonyl have even low stretching frequency, that lies between 1620 around centimeter inverse. So from the data we can suggest that this is mu2 carbonyl most probably. Okay, so just now we count the total electron. So for 2 nickel there is 2 into 10 For 2 cyclopentadiene ligand, there is 2 into 5 is 10. So now for 2 carbonyl, 2 into 2, that is 4, so we get 34. So for 2 metal ion, there is 2 into 18, we get 36, which is subtracted by 34, so we get 2 by 2, that is 1. So if you remember, there is 1 in bond, nickel bond, and there is 2 carbonyls are bridged carbonyl. It has been asked in GATE 2007 probably. So after that, these 4 complexes again asked in a question. Now this is sandwich complex. This is divided into 6 mode. So 2 into 6, that is 12, and chromium has 6 in its valence shell. So we get 18 into 2, satisfied. Here for hydrogen there is 1, for manganese there is 7, for carbon there is 10, for negative charge there is 1, so we get 19. Okay, so 19 electrons was there. After that, this compound, so this is CH3CHO, it is like this one has been donated, so carbon has only 1 electron, which thus bonded to the rhodium center, so it donates just 1 electron. So rhodium have 9 electron in its valence shell, carbon donates 2, I3, each of the iodine donates 3, each of the iodine donates 1 of each, so 3 plus 1 negative charge, so we get 16. And now from this complex we get CP, that is cyclopentadiene ligand, we get 5, from iron we get 8, from 2 carbonyl we get 4, from 1 CH3, you know that donates 1, so we get 12, 17, 18, 18 satisfied.